Here we are, okay?
Yes, now it's perfect now.
Nice. So thank you very much, Alejandro, for the invitation and also this very fascinating webinar. I've seen all the week very great talks. Thank you, Mark, for all the practical aspects and help. So I'm very happy to be there to present the result of a project that has been done by a group of people. I will detail this later. And I'm going to present today the results of two great PhDs, François Cadieux and Sakris Tambio. So what has been our goals? Well, to better understand the relationships between the electrode formulation, its microstructure, its properties, and its performance. I think many people during these webinars have the same goal. This is difficult because you know that battery electrodes are very complex composite materials, but it's really go further into the interpretation, into the understanding of these relationships, because for today applications such as the batteries for electric vehicles. So it has been, for example, shown yesterday by Janine Lee that it is desirable to increase the loading of the electrode, because this way we could minimize the amount of inactive parts in the cells, such as the separators and the collectors, that would allow us to increase the volumetric energy density and also to minimize the cost of the kilowatt hour. Here, this is a calculation based on material cost. But the problem is that thick or heavy loaded electrode and also dense electrode to have a high volumetric energy density are having strong power limitations. So we need to better understand, better characterize, and in particular to better understand their multi-scale ionic and electronic transports, to shed better light on their power performance limitation. So we are more on the experimental side than most of the talks that have been presented this week. Our goal is first to provide some kind of simple model for a final interpretation of electrochemical performance limitation for experimentalists and also for engineers. And we wish also to feed people like you, Alejandro, and others who are doing excellent modeling with very accurate and comprehensive experimental data to help you to improve these fantastic models. So what I'm going to present today is the result of an ANR project, the PEPIT project. We had several work packages. I'm going to describe them very quickly. The first work package was to design the electrodes of this project. Then we had a work package designed dedicated to the measurements of the charge transport properties with two sophisticated techniques, broadband electric spectroscopy and diffusion NMR. At the Matthijs laboratory of Eric Meyer, we've done the quantitative analysis of materials microstructure. We've done standard also electrochemical measurements, as well as electrochemical impedance spectroscopy measurements and modeling. A little bit of electrochemical modeling, but we haven't been very far in that direction. And we've also done some numerical simulations of the ionic and electronic conductivities. So I'm going to discuss today about our results that are highlighted in bold. So François has been in charge and has nicely done all the analysis of microstructure and numerical simulation, and Sakris was in charge of the doing and also interpretation of the electrochemical measurements, as well as diffusion NMR, but I will not speak a lot about that today. So here is the outline of my talk. I will first describe the electrodes that were designed for this project. They have an EV design. They were designed for electric vehicle application. I will describe their microstructures thanks to nanotomography. Then the results of the Fourier-based numerical simulations, mostly on the ionic part. Then show our electrochemical measurements and the modeling we've done, the simple analytical model that is taking into consideration only the ionic limitations. So first, to mention that we have used different techniques to characterize the electrodes at their different scales, starting with X-ray tomography to look at large features such as the whole electrode or the row powder. And then we have decreased the voxel size going to 10 nanometer with FIPSEM nanotomography. But in this case, the size of the volume was much smaller than the entire electrode. So I will not give any experimental details about segmentation, labeling, image analysis. Everything is well described in this recent paper. So here are the electrodes that were designed for this project. Let's look at the box in red. So they are made with NMC 532. You see that there are two series of electrodes. The first one, we call it the NAX, is containing a low amount of PVDF and CB. You can see the numbers here. And the second series is having that we call NAXB, is having a higher amount of PVDF and CB. Also, some electrodes have a moderate porosity, nearly 30%, and others are more dense, about 20% porosity. And okay, so you can see here some SEM pictures of the electrode cross sections, and you have here the cluster, NMC cluster size distribution. So in the raw powder, the NMC cluster has a mean particle cluster size of 5 micrometer. You see that some of them are hollow, and what is can be observed in the high density electrodes is that a significant part of the NMC clusters have been fragmented into smaller particles, in fact, primary particles, due to fracture at the grain boundaries. So you see that the mean particle size is decreased a little bit. What can be observed is an increase of the smaller particle. And this fragmentation is really significant because when you quantify the ratio of the fractured clusters over the non-fractured ones, you see that more than half of the clusters have been fractured. So this is something to input in the models to take into consideration this fragmentation, because you will see it has a significant influence on the ionic transport properties and then on performance. So when you speak about FIPSEM nanotomography and the size of the volume that have been looked at, you must discuss about the representativity. And indeed, what we found is that there are deviations between the FIPSEM volume and the electrode compositions, which is nearly for 100% sure due to local variation in the composition of the electrode and not due to a problem of precision, because the voxel size of our FIPSEM nanotomography is 10 nanometer. That is to say, lower than the size of all objects of interest. It is known, for example, that the smallest features, the nanopores into the CB-PVDF domains, are larger than 20 nanometer. So these deviations, they can be illustrated by looking at this table. For example, these two electrodes, Na2 and Na3, they have the same volumetric composition, overall composition of the macro scale. And they have, for example, 65% of NMC. And you see that the Na2 electrode is richer in NMC, while the Na3 is poorer in NMC than the macro scale composition. The counterpart is that the Na2 electrode has a lower porosity than at the macro scale, which is 28%, while the Na3 has a higher porosity. Whatever the FIPSEM volumes, we observed that the CB-PVDF content is 20 to 50% lower than the overall composition, which can be attributed to the occurrence of, see there on this large cross-section, to the very large CB-PVDF agglomerates, which suggests that the manufacture of the electrodes were not fully optimized. So because we have a discrepancy between the volume composition of the FIPSEM volumes and the corresponding electrode, all what we observed on the FIPSEM volumes cannot be directly extrapolated to the corresponding electrodes. But because we have studied different FIPSM volumes, we were able to establish trends or relationships, for example, the dependence of a property with a phase volume given phase volume fraction. And then we have used these trends or relationships to better understand the electrodes, but this time taking into consideration the true volume fraction in the electrode. So to speak a little bit about these Fourier-based numerical simulations, the peculiarity is that they are computed directly on the regular grid represented by the voxels in the 3D volume. That means you don't have to do any meshing. So I will not be able to give more details about these Fourier-based simulations. They are well described, for example, in these two papers. So to simulate, to calculate the effective conductivities, we have used the simple homogenized Ohm's law, where for each voxel, it was given the conductivity of the phase that is making this voxel. In terms of hypothesis for electronic conductivity, we've considered all contacts as to be perfect. And we have also considered the phase continuity, that this one is assumed to occur when two voxels pertaining to the same phase are touching by their faces. And we have also considered, obviously, no established cell concentration gradient, which is an oversimplification with respect to what's going on in an electrode under operation. However, I think that what we saw can be clearly transposed to what's going on when there is the establishment of a concentration salt gradient. You will see. So now I would like to describe our results about the effective ionic transport properties. I will not discuss our results about electronic transport properties today. So you will see that we have focused on the different kind of porosities that are occurring in these dense electrodes and looked at their local tortuosity. We have also done some numerical simulations, and you will see, this is the take-home message, the significant influence of the percolated micrometric porosity on the ionic transport properties. So first, let's look at these 2D slices. This is after phase segmentation, and there we have differentiated the different porosities. First, you can observe in green what we have defined as micrometric porosity. This one was segmented by setting an arbitrary threshold at 60 nanometer. This is a visually arbitrarily set threshold. So these micrometric pores, most of them can be observed at interstices between NMC clusters. So they are the void inside the NMC skeleton. Some micrometric pores are also observed inside hollow clusters, unfractured one. In this case, this type of porosity is defined as closed porosity. And there are also some micrometric pores, yes, inside hollow clusters, but fragmented clusters. But these pores, this porosity can only be accessed through, you can see here these red pores that are the nanochannels observed at the crack grain boundaries inside these NMC clusters. And finally, you have these blue pores that is the nanoporosity inside the CB PVDF domains. So if you do the quantification, you see that the micrometric porosity is the main part of the total porosity. But if you look at the denser electrode, you see that, for example, among the 5 volumes we have studied, the denser one, the micrometric porosity is only 78% of the total porosity. And then if you remove these ones that are inside clusters and are not directly in contact with the rest of the micropores through micropores, there is a kind of interface here. The junction here is only through nanopores. We have removed this part to quantify what we call the percolated micrometric porosity, which is lower than the micrometric porosity. And you see that for the denser electrode, the percolated micrometric porosity is only 72% of the total porosity. That gives, for example, for the densest volume, which is 20% porous, it contains only 14% of percolated micrometric channels, which is important, you will see. So then, as numerous previous speakers this week, we have addressed the question of the tortuosity factor, which takes into account all the aspects that are hindering the ion transport through the electrolyte within the electrode porosity. So obviously, one of the first aspects is the geometrical restriction, which can be calculated through the tortuosity, the geometrical tortuosity. But of course, there are other aspects such as interfaces. There are numerous interfaces, in particular in nanopores. And you know that ions can adsorb at the surface of solids, and also ions can accumulate at bottlenecks between large pores, for example. So here we have, on the FIPSM volumes, we have focused on the geometrical tortuosity. So it was calculated through a front propagation method. And in the end, we obtain a map where each voxel of the considered phase is allocated with the tortuosity value of the shortest path that goes through it. So on the following slide, we will first look at the distribution of the local geometric tortuosities. They are plotted here for low density and high density electrode, in blue for the total porosity, in red for the micrometric porosity, and in green when it was measurable or when the calculation could be done, because this phase was large enough. It is plotted also for the CB-PVDF mixture, the porosity within the CB-PVDF mixture. So the first conclusion is that the CB-PVDF nanoporosity is much more tortuous than the other. It is more tortuous than the micrometric porosity. But what is surprising at first sight, looking at the result at first glance, is to see that the tortuosity of the total porosity is lower than the two others. It is not a mean value. So this can be better understood when you look here at these 3D tortuosity maps. They've been obtained by thresholding to tortuosities around plus or minus 1%, the most frequent value that corresponds to these maximum there in the tortuosity distribution. Thus, these maps, they highlight the most represented tortuosities areas, that is to say, the one that should the most significantly impact the ionic transport. So in these low density electrodes, you can observe in red, the manifestation of the micrometric channels. You can see that they are wide. So here it's 10 micrometer thickness. They are wide, they are straight and low tortuosity. So likely they will influence significantly, they will allow for, they will be efficient area for electrolyte species diffusion. And you can see that in a low density electrode, the area for total porosity and the micrometric porosity are similar, but in a high density electrode, the area in blue, which correspond to the most represented tortuosity value for the total porosity, is covering a much wider area than the one for the micrometric porosity. This simply underlines the fact that between the micrometric channels in high density electrode, you have nanopores that are forming shortcuts and that are connecting all these micropores. But it is likely that during battery operation, because these nanopores are small, they will play the role of bottlenecks. So maybe that during battery operation, the effective porosity may reduce to the micrometric porosity. We will see this later. So here are the results for the numerical Fourier-based simulations. On the left, you have plotted the effective conductivity as a function of the porosity. So for the FIPSM volumes, the results are the blue dots. They are well fitted by an Archie's law with an exponent equal to 2, which is an acceptable expected exponent for such a porous composite medium. And we have a good agreement with for the moment, the only experimental value we have at the moment. Others are coming, but it's not easy to discriminate between the ionic conductivity and the electronic conductivity in a composite electrode that is containing the electrolyte and the CB-PVDF domain. So at the moment, we have only one data, one experimental result, but it in fair agreement with the simulations. And on the right, we have calculated the corresponding tortuosity factors through this equation. So the classical equation, the results are plotted in blue, and they are compared to trends results from the literature. The first ones were obtained by Useglio Vireta and other speakers this week, Mistry and Cooper. So our results are in between their two bonds. So their bonds, if I remember well, were obtained by numerical simulations on electrode architecture that were reconstructed from X-ray tomography with the CB-PVDF domains mathematically generated with two hypotheses. For the lower bond, the CB-PVDF domains were distributed as layers at the surface of the NMC clusters, while for the higher bond, these domains are more protruding into the porosity. So our results are in between these two bonds. Maybe, and also for the denser electrode, our result is closer to the higher bond, maybe because in our case we have NMC clusters and the small NMC particles that in some way are also protruding into the porosity. And our results are also compared with experimental values from Zacharias and Torat that were obtained for LiCO2 and LiFePO4 based electrodes. Their measurements were for electrodes that were 30% and less and more porous. So we have extrapolated their trends, but we have a fine, an acceptable, good agreement. So we are fairly confident with, happy with our simulations. So because we are confident in these simulations, we are now looking at more locally what's going on. And here you have a current density map. The potential difference that was applied to realize this simulation is perpendicular to these 2D slices, and the color is showing you where the current is mild or medium in blue, from where the current is high in red or yellow bright. And you have here the current density distribution. When you look at these pictures and the values, you realize that the major part of the current is crossing the micropores, the micrometric channels. There are some micropores in which the current density is high. It's because these micropores are small and they are downstream larger pores. So they are forming bottlenecks. And you can also observe that in the nanopores, you may have a high density current, but these nanopores represent a very tiny volume of the total porosity, so they likely don't play a major role. What you can also observe is that inside the hollow fractured clusters, there's a fraction of micropores that are crossed by a low current in black here. And as a matter of fact, if you look at the distribution, you can see that here there is a certain amount of porosity that is crossed by a zero current or a negligible current. So we have set an arbitrarily threshold of 0.05 ampere per square meter. And when you compare the amount of the porosity that is crossed by a current density higher than 0.05 ampere per square meter, you realize that it matches the amount of percolated microporosity. So here, this is another evidence that ionic transport is likely dominated by the low tortuosity micrometric channels through the electrodes. So now let's compare, let's inject these interpretations into the electrochemical data. So we have made measurements at 0, 22, and 40 degrees C at various C rates, and we have analyzed our results with the limited penetration depth model. And you will see that again, we end with the conclusion that what is leading the game is very likely the percolated micrometric porosity. So we've done these measurements in half cells, so versus lithium, with the LP30 electrolyte and the glass fiber separator. So to refresh your mind about the different electrodes, you have Na2 and Na7 in bold and full line here. These are electrodes that are containing the less CbP-VDF compared to Na2b and Na7b, and that appear here in dotted lines. And also in green are electrodes with the higher porosity, 28, 26, and in blue with the lower porosity, 21, 19. All electrodes have same loading, 25 milligram per centimeter square. So they are fairly thick electrode, not ultra thick, but thick electrodes. So when you look at the discharge capacity versus the current density, you see that at a certain current density, specific current density, you have brutal drop of capacity, which is a manifestation of ionic transport limitations. This is well identified in the literature. And when you look at this region, first, you can observe that these are the electrodes that are containing the less CbP-VDF that are showing the better performance. What I have not shown there, but what we have observed from electrical measurements and also by looking at the percolation of the CbP-VDF domains inside the FIPS and volumes, is that the electrodes that are containing the less CbP-VDF are not percolated. We are below the percolation threshold. However, they are showing the better performance. This is different from what has been shown, for example, at the beginning of this week for the NMC 111 based electrode. Here we are dealing with the NMC 532 based electrode, and this active material has a higher conductivity due to a higher nickel content. So we found here that for this material, it is not necessary to have enough CbP-VDF to be above the percolation threshold. If you put CbP-VDF to be above the percolation threshold, in fact, you obtain lower performance. Here, the added value of the CbP-VDF is to create gateways between the NMC clusters to avoid their strong contact resistance between the NMC clusters at the junction. So now we can observe the results as a function of the temperature, 0, 22, and 40 degrees C. So as expected, at least for Na2 and Na7, we observe the significant improvement of the capacity at 1.7 C that corresponds here to this vertical. So big improvement with increase of the temperature. This is also observed for the electrode with the higher amount of CbP-VDF between 0 and 22, but here then fairly surprisingly, unexpectedly, you observed nearly a leveling of the performance for Na7b or a decrease for Na2b. I'll be back to this later. So now I would like to address a little bit this limited penetration depth model. So this one accounts for the formation of the lithium salt concentration gradient across the cell, which is illustrated here. This is a plot from a pioneer work by Fuller, Doyle, and Neumann, where you see the lithium salt concentration at the beginning of discharge and during discharge, and you can realize here at the end of discharge, or at some point of the discharge, the lithium salt concentration has dropped to 0 at the bottom part of the electrode. That means this part of the electrode cannot further proceed with the electrochemical reaction because there is no more available lithium for insertion. And if you go to higher rate, this area here will appear sooner during discharge and will also be of the largest size. So building on the work by Fuller, Doyle, and Neumann, Jones and Gallagher have established this simple equation to determine this limited penetration depth as a function of the electrode porosity, its tortuosity factor, the diffusivity of the electrolyte, its salt concentration, the transference number for the lithium cation, and also the applied current density. And if you have no solid state mass transport limitation, if you have no electronic conductivity limitation, then you can calculate, estimate, let's say, this is an approximate model, you can estimate the accessible capacity by simply comparing this limited penetration depth to the electrode thickness, and also taking into account the specific nominal capacity. So we have fitted, Lestriez has fitted its electrochemical data with this model. Some examples are shown here for the Na7 electrode at the 3 temperatures. So you see that the model well predict, let's say, the brutal capacity drop for a certain current. There is the model does not allow to predict the capacity below this current, this A star current, because it only considers the ionic transport limitation. This is also the reason why there is a discrepancy at very high rate, because the model does not also take into account the large cell polarization at high rate, which is also responsible for which add some capacity loss. So how have we done this fitting? Well, in fact we have values to put inside this all the parameters for this equation, because we know the porosity, we have calculated estimated tortuosity factors and so on. But what we have decided first to do is to do the fitting by fixing some variable and allowing one of the parameter to vary, to really nicely match the experimental data. And we started with the diffusion coefficient. So we have done the fitting with considering the total electrode porosity and considering either the tortuosity factors determined by numerical simulations, or taking values from the literature. Here I'm showing the results where we consider the lower bound of Usiglio-Vireta. So here are plotted the effective diffusion coefficients, the values extracted from the fit, as a function of the temperature for the various electrodes, and compared to the bulk lithium diffusion coefficient. So first, we were happy to see that we obtain good order of values for the diffusion coefficients, and we reproduce the temperature dependence to some extent, except for some electrodes. I'll be back to that later. But if you look at the values, they are to some extent too high, let's say, compared to the bulk value. For example, for Na7, the extracted diffusion coefficient is 3 times higher than the bulk value, which is difficult to conceptualize. We would have expected rather to find lower diffusion coefficients from the fit compared to the bulk value, because we are taking into consideration here we were expected that maybe some additional limitations we don't know, such as interfacial effects or others, would have resulted in decrease of the diffusion coefficient. And also what you can see is that the extracted values, they all depend on the electrode formulation. So this invited us to look at things differently. And then we have considered as the variable parameter the tortuosity factor. We considered the total porosity and the bulk electrolyte diffusivity. The results are here plotted for the 4 electrodes for the different temperatures, and they are compared with the geometrical tortuosity factor values for the micrometric porosity and for the CB-PVDF domains. So for most of the electrodes, and considering the various temperatures, you can see that the effective tortuosity factors are in between, that for the micrometric porosity and that for the CB-PVDF domains, which is an interesting result, because we could have expected that the effective tortuosity factor would be a mean value representing the whole of the architecture. But if you look more closely, you see, for example, for Na2 and Na7 at 0 and 22 degrees C, or Na2b and Na7b at 0 degrees C, that the effective tortuosity factor is very close to that of the micrometric porosity, suggesting that at these temperatures, it is the micrometric porosity that is leading the game. And you can also observe that for the electrodes that are containing the minimum amount of CBP-VDF, there is an increase of the tortuosity factor at 40 degrees C. And also for electrodes with the higher amount of CBP-VDF, you have very significant increase of the tortuosity factor with the temperature. So we only have an interpretation based on previous studies and also some evidences we got by doing some NMR measurements that it might be due to the selective adsorption swelling of the PVDF phase by the EC-DMC electrolyte solvent. In this case, and the swelling can be very significant at 40 degrees C. And what we believe is that if you have a swelling of the PVDF phase, you will have a swelling enlargement of the CB-PVDF domains, which may result in the closing of certain pores. See, for example, these micropores here or there. If you have an expansion of the PVDF domain, and if you have a gelification of the PVDF by the electrolyte solvent, you will form there some microgels with a very high viscosity that will really hinder the diffusion of electrolyte spaces at this point, and thus you have a kind of loss of percolation at that point. So this suggested us to play with the model in a last way, where we have considered as diffusion coefficient that for the bulk electrolyte, consider the micrometric, the tortuosity factor as being equal to the micrometric porosity, because for all what we've seen before, this is what is playing the game. And then we have used the porosity as the variable. So the results are shown here for the 4 electrodes, again as a function of the temperature, and they are compared to the total porosity, the line, the upper line, and the percolated micrometric porosity, the lower line. In all cases, the effective porosity appears lower than the total porosity. And for some electrodes, in particular Na7, Na7b at low temperature, or Na2b at low temperature also, you see that the effective porosity seems to reduce to the percolated micrometric porosity, in fact. For other electrodes, in particular Na2b and Na7b, you have a strong decrease of the effective porosity, which is in agreement with our hypothesis, that is to say that this is the micrometric porosity that is leading the game, that is the most important to homogeneize the lithium salt concentration gradient, and that the swelling of the CB-PVDF phase may result in the loss of percolation at some point in this micrometric network. So we are not 100% sure, but this is, I think, an interesting way to look at the behavior of these electrodes. So I'm at the end. So to conclude, we've seen that these dense NMC electrodes, they are characterized by a significant fraction of NMC clusters that results in large distribution of porosity. That the effective tortuosity factor is a complex parameter. This is absolutely not new, but we confirm it. And that a single and mean value may not be representative of the influence of the microstructure on the ionic transport. These NMC 532 electrodes with low CB-PVDF amounts below the percolation threshold mixture, they show good performance, better performance than for higher CB-PVDF amounts above the percolation threshold. So this penetration depth model is not from us, but we have brought some improvement in this model or its use, and we may say that it is a simple analytical model and interesting to address the origin of power performance limitations. We would like to stress the importance of the swelling of the CB-PVDF domains that appears to be fairly detrimental to the power performance because they restrict the effective porosity, and that at high rate, this effective porosity appears to be reduced to the percolated micrometric porosity, which is influenced by the CB-PVDF swelling. So I'm really acknowledging all the people that have contributed to this project, and in particular François and Sacris for their very nice work, and also the funding organization. All right.
Thank you very much, Bernard, for this great presentation. So I will confess you something. When I mean, for writing the artistic project, I was very inspired by your experimental work. So because, I mean, it's amazing. Always very systematic study of the influence of different parameters. Thank you very much. It was great.
Thank you, Alejandro. And now you are doing magic work.
Thank you. Thank you. Okay, so there is several questions waiting for you in the question session.
Yeah.
If you go to a question session, I mean, you can click on start a live answer, and then the question will appear in the screen, and then everyone will see the question, and then you can answer the question. I can do for you if you want, but yeah, great.
Okay. So can you read the question, because my throat is...
Yes, no problem. So have you experimentally found a way to reduce these PVDF CB agglomerates?
Okay, so the point is that we haven't done ourselves these electrodes. They've been provided to us by Renault. So I guess it should be possible to, because this is something which is not usual to observe in electrodes. What is interesting, finally, is that it says to us that we can even put less CB-PVDF than was put at the big in these slurry receipts to achieve good performance. This is what I can say.
Okay. So maybe you can, I think, minimize the question. Mark?
Yeah.
You have to do that?
It is Anna who used to do it. I have not the handle on that.
Okay.
Okay.
Great. Now you can click another one.
I understand.
I missed your first part. So maybe you already mentioned the first part of your presentation, but how could you conclude whether the CB is below the percolation threshold?
Okay, so I haven't shown this here, but yes, simply by looking at the geometrical connectivity of the CB-PVDF domains, it was 100% for sure that they are distributed and not connected to each other. And also when we have done electrical measurements, it was very clear that for the electrodes which are containing the higher amount of CB-PVDF, that the activation energy was metal-like conductivity, that is to say, typical of CB-PVDF above the percolation threshold, while for the electrodes that are below the percolation threshold with low amount of CB-PVDF, the activation of energy was a mix of the activation energy of CB and NMC. Okay.
Are the results in this presentation available in a publication?
So 2/3 of the results are available in publication, one already accepted, one which is submitted, and the third one is under writing.
So do you have any study over metal dissolution in the cathode, crack generation in electrode particle, and further changes in porosity of cathode particles?
So this is an excellent question. The other questions are also very good, but this one is excellent, maybe because I haven't thought of it. So yes, because this cracking may release some transition metal. We haven't looked at that, but I think this is likely very important, in particular for the cyclability of these electrodes. So thank you very much for this question. And what I can say also that we haven't looked at the morphology of the electrode after cycling, because we were really focused on the power performance, but that would have been great. Yeah.
Thank you very much. Do you consider the alleviation of brutal capacity drop at high temperature is due to decreased activation energy following Arrhenius behavior?
Yes. So at higher, so due to the Arrhenius behavior, you have faster diffusion at high temperature. So to some extent, we are observing better electrochemical performance, but this is mitigated in the case of high CB PVDF content, due likely to the swelling of the PVDF domains by the electrolyte.
Have you looked at the response of similar NMC electrodes with a binder that does not swell in the electrolyte?
So we've got some data, but we haven't yet looked at that. I guess that for electrodes prepared in water with CMC binder, for example, maybe we could have an answer about that. But this might be an added value of the aqueous binders that are less compatible with the electrolyte at high temperature. I was hoping Marie Bichon would have the time to do that, but she finished her PhD before.
Good. So there are some other questions in the chat. I can read for you if you want, because
Yeah.
there are mixed comments. Is there any replay video? Yes, we can answer is yes. So we are reading.
Yes. but we will give our agreement.
For sure. So we will ask agreement before, and we can edit the videos as well. I mean, just to only keep the parts that you agree with that. So Emiliano Primo in the chat is asking, from slide 9, I was wondering if you quantify this deviation of porosity from fifth SEM from the macro porosity calculate with the densities. Is there any minimal amount of image you should take to match these values, or maybe there is a limitation with the calculation of macro porosity?
Okay. So if I'm going to slide 9, right? The porosity was, the macro porosity was simply calculated given the size and mass of the electrode. So this is really an average porosity. For each electrode, we only have one fifth SEM volume because you know that it is very costly in time and efforts to do the segmentation. And we know that they are not 100% representative. What we just are saying here is that, yes, they are not representative, and to have some fifth SEM volumes or some data extracted from fifth SEM tomography to be representative of the corresponding electrode, we would need either much larger volumes or more numerous ones to achieve mean values.
Good. So there is another question from Emiliano, slide 14. Could you please give further details on the procedure for calculating this local tortuosity? Yes,
I will try. Okay, to calculate, okay. So the method is to some extent explained here. What is done is to move a propagation front from one side of the volume, and you calculate the distance, and you can do the same from the other side, and then you end up you sum the two, and you end up with a map where each voxel is given the tortuosity of the shorter path that is going through this voxel. So what is represented on the slide 14 are the distribution of the local tortuosity, that is to say the tortuosity values for all the voxels.
Good.
Yeah.
So there is a question from Ulrike Kroe. Do you use also electrochemical impedance spectroscopy for parametrization? This should aid in identification of a unique parameter set.
Sure. So we have done some electrochemical impedance measurements, but not enough. It is my big regret because it would have been very nice to be able to match the impedance spectra with to make some correspondence with the true architectures, the real architectures. Yeah.
Good. So I think we are a bit late, Bernard. So I propose we stop here. You still have some questions pending. So if you go to the chat, there is a question of Teo Lombardo. I'm sorry, Teo. I mean, for time reasons, I cannot give you the flow for the answer now. And also, there is some questions waiting for you in the question session, and then you can reply just by writing, directly.
Okay.
Thank you very much, Bernard, again for your great presentation today.
You're welcome.